So we had looked at the idea of some vector and some other vector b. And we've thought about vectors. We've talked about what they mean in terms of a direction and a length. But we had also said that if you had two vectors that were put together like this, that you could calculate the area of the parallelogram that they form by doing what? A cross product, right? We could have a cross product of A and B, but we would have to think of A and B as what kind of vectors? Three-dimensional, right? So three-dimensional vectors. And then what would the cross product be? What kind of thing is it? Cross product is also a vector, isn't it? But what is the area of a parallelogram? It's a scalar, right? It's a number. And so what do we have to do to this cross product to get the area of that parallelogram? To get the area, it was the length of that cross product. So we'll think back and refresh that. But we can find the area of a parallelogram by finding the cross product of the two vectors that form the parallelogram. If it's a two-dimensional, we need to make it 3. So how do we make it a three-dimensional vector? Add a 0 as the third component. If it's already three-dimensional, then we don't need to make that change. But the parallelogram itself is this two-dimensional object. And the area was the length of that cross product. All right, so that's one approach. That's something that involves, remember the idea was that we calculated the height of the parallelogram, and the height was based on the sine of the angle, and the cross product has the sine of the angle built into it, so all of this stuff is built in. And so we can calculate, but that's maybe a lot of overhead. What if we had the A and B, and we wanted the triangle that they formed? We wanted the area of the triangle. How would we calculate that? What do we know about that triangle in that parallelogram? That triangle is half of that parallelogram, isn't it? So what could we do? We can do this to get the area of the triangle. All right, so let's take a look at a triangle. Let's say we had a right triangle. Let's say this was a 3, 4, 5 triangle. If we want the area of that, what do we do? Right? You say 1/2 base times the height. And we think of, usually in this kind of situation, what would we think of as the base? We would think of this side as being the base probably, right? So this is the base, and this would be the height. And so 1/2 times 3 times 4. So the area of this triangle is 6. Right? 1/2 times 3 times 4. Well, what would happen if that triangle were turned like that instead? Then 3 is the height and 4 is the base, and it still gives us the same number. What if it were turned like that? Now 5's the base, and what would we have to do? Try to figure out what the height is, right? We'd have to solve for something to figure out what the height is. All right, so how would we solve that to figure out what the height is? Well, to get that height, here's this angle, theta, and we need the height. So I'm going to redraw that here. This is the height that we want, and here's the angle theta. can we figure out that height? What else do we know about this triangle down here? Which sides do we know the measurements of? We know the top. What is the measurement of the top? That would be the 4, right? Because the 3 is the shorter one, 4 is the midsize, and 5 is this one. So this would be 4. And this is h. We don't know what h is, and we don't know what this side is. And we don't know what the angle is. But can we figure out what the angle is? Let's take this. Rotate this back around here. This was this angle up here. And what do we know? This was 3, this was 4, and this was 5. Can we find out anything about that angle? What can we do? We could look at sine of the angle. What would sine of that angle be? Well, sine's going to be opposite, so it would be 3 over 5. And cosine would be the adjacent of it, so cosine would be 4 over 5. So what could we do? We could use the arc sine or the arc cosine and get the angle, and then put that angle up here and have what? Sine of the angle is h over 4. So what could we do? Well, we could take the sine, put that here. We already have this. We don't have to do the arc cosine. We could just take the value and put it there and solve for h. Then we would have the height multiplied by 5. All right, so what happens? Sine of theta is 3 over 5, which is h over 4. So what is h? Multiply both sides by 4 would be 12 over 5. And what would the area then be? The area would be 1/2 times the base, which the way that was turned was 5, times the height, which is 12 over 5, which is still 6, which is exactly the answer that we thought it should be all along. Right? So it's still the same answer. It doesn't matter how you've turned the rectangle or turned the triangle, it does not change its area. You can move it and turn it, and it doesn't change. It's just that what happens in that particular approach, if we didn't notice that it was a right triangle, it looks like there's a lot more work. And there would have been even more work had this not been a right triangle, because we wouldn't have had this easy aspect here. But we could still make some progress. All right, so often the way we are looking at it will determine how difficult a problem is. If we've turned it a certain way or turned it a different way, something can become easier. Well, there's another method for calculating the area of a triangle called Heron's formula. And Heron, from what I can tell, was born in Alexandria in like 62 BCE. So we're talking a couple thousand years ago. I don't know that Heron discovered the formula. Lots of times things are named after someone that just was responsible for making them popular. So maybe someone wrote something about it or talked about something a lot. And so things get named after the wrong person a lot. So I don't know the history on that particular formula. But the idea here is if we have a triangle, let's say it has sides A, B, and C. It doesn't have to be a right triangle, just any triangle with sides length A, B, and C. We first calculate the semi-perimeter. All right, so what does perimeter of a triangle mean? Adding all the lengths together, right? So the semi-perimeter starts with that, adding all the lengths, but then divides by 2. All right, so add all the lengths and then divide by 2. So that's the semi-perimeter. And so the formula says that the area of the triangle, now the area of the triangle involves half times the base times the height, but this is going to hide that inside there. what we will do is we will take this semiperimeter S and then multiply by S minus A, then multiply by S minus B, and multiply that by S minus C. Now let's think about A, and we're not quite done, but let's think about A. What kind of thing is A? A is a length, so maybe it's meters. And then B and C are also in meters, so what is S? What are the units of S? It's also meters, right? Meters plus meters is still meters. Divide that by 2, it's still meters. So what are the units of this thing, this number? Meters times meters times meters times meters is meters to the 4th. 1, 2, 3, 4 of them, right? Meters to the 4th. Well, what kind of answer are we looking for with the area of a triangle? Meters squared. So what do? Take the square root of that. All right, so this is Heron's formula. Well, let's see if it's even believable. Let's look at our 3, 4, 5 situation again. All right, so what's the semiperimeter? Semiperimeter is 3 plus 4 plus 5 over 2, which is 6. And so the formula says that we're going to have the square root of 6 times 6 minus 3 times 6 minus 4 times 6 minus 5. Six times 3 times which is the square root of 36, which is 6. And so at least in that example, it gives the right answer. Now it could be that this is only reserved for right triangles, but let's take a look and see what else we can do with this. All right. So now where this comes from, don't worry about it right now. If you really want to know and you really want to be able to prove this, then we can do that. Maybe individually might be better than as a group, because it's not, for us, it's more of a tool that we can trust, but it is often nice to be able to confirm that something is valid.
Should there be parentheses around the semiperimeter formula?
You mean around the whole thing?
No, semiperimeter, like A plus B plus C.
Well, if you've written it this way, it's not necessary, because all of this is over that. But if you've written it like that, then it is necessary. So in that particular way, you don't have to have the parentheses because it's this thing divided by that thing. But if you were writing it, say, a function, then you would need that. All right, so let's take a look at a situation that's not so easy for us. All right, the other day we were talking about a triangle, and I drew this and asked you if it was a triangle. And what did we decide? That it's not a triangle, right? We have a bad drawing. You cannot have a triangle with sides of length 1, 2, and 4. Could we have, again, the reason for that is because the 1 and the 2 aren't long enough to touch. Even if you lay them down flat, they don't reach each other, so we can't actually form that peak. What about a triangle with sides length 3, 5, and 6? Is that possible? Yes as a question or yes as a statement? Well, let's think about what has to happen to make a triangle. Any two of the sides, if you add their lengths together, they have to, that sum has to be greater than the third one, right? So 3 plus 5 is 8, that's bigger than 6. 3 plus 6 is 9, that's bigger than 5. 5 plus 6 is 11, that's bigger than 3. So yes, we do have a triangle that has these lengths on the side. Now I'm going to put the 5 just in that direction again. And let's think about what the triangle actually has to look like. Can it look like that? No. What would have to happen? 3, if we're coming from this end, let's say, the 3 would have to go off like that, wouldn't it? And then the 6. Because otherwise, this side isn't the longest side in the triangle anymore, right? So it looks something like this. And again, not to scale, but it looks something like this. Now let's say we want the area of this triangle. All right, so to find the area of this triangle, we have 3 different ways to do this. If we trust Heron, what can we do? So S would be 3 plus 5 plus 6 divided by 2, which is 7. And then the area would be 7 times 7 minus 3 times 7 minus 5 times 7 minus 6, and then the square root of all of that, which is square root of 7 times 4 times 2 times 1. And what is 7 times 4 times 2 times 1? All right, so the answer then would be the square root of 56, and we'll leave it at that. Right now, we won't try to simplify that any further, right? So according to Heron's formula, the area of this triangle is the square root of 56. We have no reason to believe that. We have no reason not to believe that, right? We don't know. We have a formula that somebody told us. Well, let's see if we can calculate this area in different ways to figure out, at least if it gave us the right answer in this case. So what other ways do we have to do this? All right, so one way is given this triangle. Have it turned this way, so we have the base is equal to 5 right now, and we need to find the height. All right, so how can we go about finding the height? Well, let's hold off on that for a second, right? That's one thing that we could do, right? If we think about the problem, we say one thing we could do is we could try to find h, and then if we can find h, we can multiply b, which is 5, times the height, divide that by 2, and that would be the area of our triangle. All right, what else could we do instead? We could have this vector and then this vector that describes that other side, and do what? Do the cross product, find the length of the cross product, divide by 2, and that would be the area as well. All right, so what do we need for this? We need to figure out that height. What do we need to be able to do this? We would need to figure out the coordinates of both of those vectors. All right, so let's think about this. Let's put this corner at the origin. Might as well put it somewhere that's nice, right? We can put it at the origin. And then this side ends at 5, 0. Now this side ends at some point xy that we don't know right now. Is that okay? Yep. Now, either of these could use that information. This could use that information because if we knew xy, what would vector b be? It would be the vector with xy, and then since we need the three-dimensional version, it'd be xy, 0. So if we can figure out what x and y are, we can use that method if we want. What would figuring out x and y, how would that help us in this case?
Figure out the height.
What would the height be? Y would be the height, right? So if we can figure out x, y, then we can use either of these two methods. We don't need x and y for this method, but we're trying to see, do they actually give the same answer? All right, so can we figure out anything about x and y from what we have here? How long is this side? 3. It's 3. And this side is 6. Well, so let's
Or
see.
-1, sorry.
Let's see what happens. The distance from this point to that point is 3, isn't it? So how do we calculate the distance from this point to this point? The distance formula says you take the x value of this one and subtract the x value of this one and square that. And then you do the same thing with the y values. You add those together and you take the square root of things. We also said to try to avoid taking square roots as long as you possibly can. So let's do this without the square root. The first part would be x minus 0 and then square that. The second part would be y minus 0 and square that. And if you don't take the square root, what do you get? What is that equal to?
3 squared.
Be 3 squared, right? That would be equal to 9. Is that okay? So it's something we know, right? I mean, I don't know how useful it is, but it's something that we know. And this is that exploration portion of what do we know, what do we not know, right? We're trying to figure it out. So at least we know something in terms of x and y. We know that x squared plus y squared is 9. So if x did turn out to be 1, what would y have to be? Well, if x was 1, then y squared would be 8, right? All right, so I mean, we have something. Well, it could be, I guess, plus or minus. There's something to consider there. What do we know about the x and y values beyond this, beyond the fact that x squared plus y squared is 9?
X would have to be negative.
X needs to be a negative number because of the direction that it's pointing relative to the origin, right? So x is negative, y is positive.
But since they're both being squared, it doesn't.
So it doesn't matter in this, but as far as the x values that we're allowed to consider, the x needs to be negative, the y itself is positive. And x squared plus y squared is 9. All right, what else can we say about x and y? We could do the same thing in this direction, couldn't we? So how far is it from this point to that point? The distance is 6. And otherwise, what could we do? We can say x minus 5 squared plus y minus 0 is equal to what?
36.
Is equal to 36. Does that make sense? So we have two pieces of information. We have x squared plus y squared equals 9. And then we have this. We also know that x is less than 0 and y is greater than 0. So we have, I guess, 4 pieces of information in all. Can we do anything with that? Well, let's see. X minus 5 quantity squared means x minus 5 times x minus 5. So what do we need to do with that left-hand part here, with this? Yeah, we need to distribute, right? We FOIL this. So what do we have? We have x squared minus 5x minus 5x again, and plus 25 plus y squared equals 36. All right, so that's x squared minus 10x plus 25 plus y squared equals 36.
Then you move over to 25.
All right, subtract 25 from both sides, and we have x squared minus 10x plus y squared equals 11. Then what?
You get the y squared on the other side of the equation. You could substitute y squared for
What do we know? We know that x squared plus y squared is 9. And there's an x squared plus y squared right there. So instead of separating this, let's bring in the other part of information that we know. What do we know? We know that negative 10x plus 9 is 11. So now what? Negative 10x is 2. So x is negative 1/5. Or if we wanted to write it as a decimal, negative 0.2. All right, so what do we have? That fits, right? X needed to be negative. It was supposed to be negative, and we didn't have to do anything. It is negative. All right, so we have our picture. This point is 5, 0. Here's the origin. And this point up here is negative 1/5 y.
So you can just put the x into the x squared plus y squared.
Yeah, so let's put that x value in here. So we get negative 0.2 squared plus y squared equals 9. What is negative 0.2 squared? Right, 0.04 plus y squared equals 9. So what is y squared? 8.96. So what is y? Since y is positive, we only need the positive portion of this. So what is y? Square root of that. Square root of 8.96. We can calculate the square root of 8.96. What is the square root of 8.96? 2.99. Let's go a little bit further. (2.9933), almost 3, right? Because this is almost 9, so it's almost 3. All right, so what do we have? We now know that this point is 5, 0. This point was 0, 0. And this point is negative 2.9933 approximately. And here's our triangle. Great, so what happens in terms of the area in this method? The area is 1/2 times the base times the height. So it's 1/2. The base is how long? Still 5. And the height? 2.9933. Instead of equals here, we should say it's approximately equal to that. And what is 1/2 times 5 times 2.9933? Well, that's 2.5 right there times almost 3. So it's going to be 7 point something. 483 if we round it to 3 decimal places. We don't need to round because we could go all the way. Be like 2.5 or something. All right, so about 7.483 is the area that we've calculated using this approach. What was the area that we calculated using Heron's formula? Square root of 56. What is the square root of 56?
7.483.
It's just about 7.483. Right, now again, there's some stuff that comes after because we rounded that, and there's more stuff after that. But what happens? This answer, using the other approach, is the same answer that we get in that way. Now, what would happen if we used the vectors? Well, what would the vectors be? Vector A, describing this side, would be what? But it needs to be three-dimensional, so put a 0. And vector B, would be this side. So negative 0.2, 2.9933, 0. And if we did the cross product and then calculated the length of that vector and then divided that by 2, you can check it. We've already proved that it works. You get the same answer. All right, so which would you want to use if you wanted the area of that particular triangle? Well, that approach took a lot less work, didn't it? Has all the same information hidden away, but it's a lot less work for us to just use those numbers if we already have them. Right? Calculating the semi-perimeter is easy. Just add 3 numbers together, divide by 2. And then the differences, those are easy to calculate. Multiplication is easy to do. The square root is involved, but in no matter which situation we have, we're going to have to do something that involves finding that height. And in this particular case, we could do the work by hand, and we only needed the square root at the very end, but there was still a square root there. And in this method, we had to get that value, so there was a square root in there as well. Right? So we can't really avoid that part at this point. All right, but what can we do? We can calculate that area without necessarily knowing anything at all about the angles. Right? The angle stuff is there, it's built in, but we don't always have to use that. We can solve, neither of these methods actually involved, none of them involved anything at all about the angles. Although they all involve something about the angles, it's just all hidden. Right? We never find out exactly what any of those angles are. And we don't need to. If we wanted to find out the angles, or if we knew something about one of the angles, then we have other approaches available to us that we could apply and solve the same problem. All right, so the question might be, though, why do we care about the area of a triangle? All right? How often do we need to calculate the area of a triangle? Let's think about some triangle. And let's say that we have a point that's inside that triangle. So this triangle, we know the triangle, say we know the coordinates of the points. So we can calculate the area of that triangle using Heron's formula or any of the other methods that we have, right? We can calculate the area of that triangle. What if we calculate the area of that triangle and then calculate the area of that triangle and then calculate the area of that triangle? What would happen? Well, what do we know about those 3 small triangle areas? We add them up, we get the same area as the big triangle originally. And remember, calculating the area of the triangle, of any individual triangle, is not that much work, right? So what happens instead if our red circle or red point is outside that triangle? Now we do this triangle. And we do, let's do them in the same order. Match them color-wise. We do this triangle and this triangle. And then we still have the blue triangle. And what happens if we add the areas of those triangles together? The red, the green, and the blue. That's bigger than the original, isn't it? Just the red and the green by themselves are bigger than the original. Does that make sense? So what happens? Since calculating the area isn't too much work, what does this let us do? This lets us test, calculating area lets us test to see if a point is inside or outside of a triangle. What would happen if the point was right on one side of the triangle? Then what would happen? We would have that triangle. We have that triangle. And what about the blue triangle? Yeah, it's not a triangle, is it? What's its area? Just a straight line. What's its area? The blue triangle has area 0. So when you add the red, the green, and the blue, what do you still get? The same area as the original, but one of those triangles had area of 0. Does that make sense? What if two of them had area of 0? Is that possible? What would that mean if two of those small triangles had area 0? Yeah, that would mean that the point was on a corner. Then what would happen? The red triangle would look like that, and then the green and blue triangles would be not really triangles, they would be lines, they would have area 0. And so if two of the pieces were 0, then a point is on the corner. If one of the pieces is 0, then the point is on the side. If neither of the pieces is 0, but the areas all match the original, the point is inside. And if the areas add up to be more, then the point is outside. All right? And so it's an easier way to check to see whether something is inside or outside a triangle, rather than seeing, okay, is it on this side of this line, and this side of that line, and this side of this line, and all that kind of, right? Worrying about which side of a line something is on when the lines aren't vertical can be more difficult. But the area will actually tell us if a point is inside of a triangle or outside of a triangle. We just need to be able to do that calculation. So what happens? Heron's formula can do that for us if we know the lengths. If we know the vectors that make it up, then we can do the dot product, or we can use whatever method we like, but the area can be part of a test for inside or outside. What does it matter if a point is inside or outside of a triangle? Collision, right? We can detect collision. So if we have something that's moving along and there's a triangle, and we know in the next frame that the areas are going to be wrong and the point's going to be inside, we can make something happen beforehand, right? We can divert it, we can make it bounce off, or whatever we need it to do. So for collision, we can use that to detect. Now, what if instead of a triangle, what if the shape were a rectangle? What's the easiest way for collision, or inside or outside in that situation? Right? It is easier to say, okay, are the x values, in the right range, and are the y values in the right range, right? Because this is oriented according to the regular axis system. Now, what if it's a shape like this? Then it might be easier to break it into two triangles and test that side and test the other side. Is it in that triangle? No. Is it in that triangle? No. Okay, then it's not inside this object. What if the shape were a circle? And you want to see if a point is inside the circle or outside the circle? Or on the circle? Yeah. Radius of the circle, the distance from that point that we're looking at to the center. If the distance is less than the radius, then it's inside. If the distance is greater than the radius, it's outside. And if the distance is equal to the radius, then it's on the circle. All right? So these two methods don't benefit, or these two situations don't benefit from area at all. But this kind of situation, or a triangle, could benefit by being able to do collision detection based on calculating areas. Probably not something that we would immediately think of, that area has anything at all to do with being able to tell whether something is inside or outside of a triangle. and then correspondingly inside or outside of a more complicated shape. But if it's inside, then the areas will match in a certain way, and if it's outside, then the particular areas will be larger. And so we can do that kind of test. All right, so some of the things that we do, we might think, well, why is that important? Why does that matter? And you realize that each piece is part of a bigger puzzle, that sometimes things have a role that we would not have expected. We would not have guessed that doing this calculation would tell us anything at all about something else. But in this particular case, we see that all the stuff about calculating area does tell us something about a bigger sense. So we're going to use this in a later lab of being able to tell if something would intersect with something else, right? Whether this thing that's traveling along, is it going to run into certain things along the way? And if it does run into something, we can change. We'll indicate that something changed. And then we'll use this in different ways, right? Some collision detection things are built in. Our idea, our goal, part of our goal is to understand how all of that works. And one way is in this probably surprising way that area can tell you a lot more than we would think area could tell us. All right, so as usual, if you have any questions, you can Discord or email or ask, right, at any time. But we want to make sure that we understand that these basic concepts so that we can use them in more and more complicated ways as we go through the rest of the term.